Einstein had this box, and it had atoms in it, and he had populations in the two levels. He had a two-level system there, and there was light inside there doing thermal radiation. It formed an equilibrium. Now what we want to do today is take this same population, and I'm going to put windows on the box, and I'm going to shoot a beam through there. And I want to see how this beam interacts with those atoms. So we still have these atoms. We've got various levels. We've got a number in state 2 and a number in state 1. Now I'm going to shine light, and I want to see how it interacts with this beam here. And so when I've got atoms up here, three things can happen. You can always have spontaneous emission. So that the light just comes out naturally. And we had a rate equation for that. Einstein gave us that. He said dN2 dt equals A21 N2. And something which you probably want to reinforce today. I'm going to shut this door. Hey, could you guys talk someplace else? Sorry. Every time an atom drops to another state, it gives off a photon. So we're going to kind of reinforce this as we go along. We're talking about populations here, but I want to kind of plant the seed that every time N2 drops, I want a photon is generated. So when I start talking about what's the change in intensity, I'm just going to multiply that by h nu and say, oh, I've just added a photon to the field. So these N2s of population correlate pretty quickly to our population of photons, if you will. Anyway, we had that one. We had stimulated emission. And that's where you get a dN2 dt was given by B21 times N2 times rho of nu. So that's what Einstein said. But remember we talked about this last week. He said, what if we probe this with a very sharp, a source with a very sharp, well-defined frequency. So here's our frequency spectrum. And we're going to come in and say with a laser beam, which is really all its energy is at one particular frequency. And we noted that the atom might have a transition which is fairly broad. And so in the black body, you have this black body radiation, there's photons all over the place, so there's photons being absorbed and emitted and interacting with all wavelengths. But if I come with one particular frequency, I got to change this. So what we added was this G of nu term. And what that G of nu was the probability that a photon will emit at that frequency or absorb at that frequency. And the key thing about the G of nu, so that we had a line shape function, and the integral of G of nu over all frequencies equal 1. So it's a probability. So we have to add a probability when we go to really narrow line sources. And we have to in a laser beam, because in a laser, only one particular frequency is going to operate. It's not a black body. It's really sharp. So we modified the equation by adding this line shape function. And then there's of course absorption. You can call it stimulated absorption if you want, because it's just a time reversal of this process. And that would be dN2 dt, equals plus, because absorption now will kick an atom from here up into N2. And it's going to be B1 to 2, N1, rho of nu, times the probability that light is absorbed. So those are the stimulated emission equations we came up with. Then we talked about the line shape function, and we kind of beat this there. We looked at lifetime broadening, and we got a shape that looked like this. So for lifetime, or more correctly for homogeneous, and do you remember what homogeneous meant? It meant every atom interacted the same. So I shine light on it, and every atom in the system had the same probability of interacting with it. So for lifetime broadening, you get something of this form. G of nu equals, I'm just going to put this down for record, 1/2 divided by 2 pi nu minus nu naught squared plus delta nu over 2 squared. So it's a Lorentzian line shape. So we get this probability like that. And delta nu is your half width. That would be measured like from here to here. That's delta nu. And for a lifetime broadened system or these kind of things, we came up with delta nu 1/2 was equal to 1 over 2 pi. It came out of the uncertainty relation. So it'd be A1 plus A2 plus your twice the collision frequency of the gas if you had such a thing. So all of these things, collisions, lifetime, they're all homogeneous broadening. And so we showed up these line shapes. Yeah?
So what's the difference between delta mu 1/2 and delta mu?
Oh, same thing.
Oh,
Same thing, yeah, thanks. So this would be for a lifetime broadened system. And there's lots of homogeneously broadened systems which don't necessarily follow the shape. And I'm thinking of phonon broadening, for example. If I look at lifetime broadening, I'm going to see this very nice symmetric shape like this. Everything's cool. If you look at some crystal, take an atom like, I'll say chrome zinc selenide. And chromium, turns out it's homogeneously broadened because it's so rapidly interacting with phonons. But its line shape kind of looks like this. So it's not symmetric. But it's got homogeneous broadening. So you've got your same delta nu, but it turns out your G of nu is, it depends on the shape here. So G of nu can be a empirically derived equation or formula. It depends on the system there. These are very nice mathematical things, and they're nice in some situations, they're not always there. So just as a warning, all homogeneous systems are not Lorentzian, and not necessarily nice-looking shapes. I've seen G of nu's which have this kind of crap like that. Okay, you just deal with it. So you can have homogeneous broadening and not smooth functions, but everyone acts the same way. So, all right, so that's that. Then we also talked about Doppler broadening, and that's an equation I didn't write down. Doppler was inhomogeneous. I just want to put this down for your, I'm sure you've been curious about it all week, right? So G of nu for a Doppler broadened system. So Doppler is when you've got gas and it's moving back and forth and you've got a distribution. So this G of nu is kind of weird. 4 log 2 over pi to the 1/2. 1 over delta nu Doppler. E to the minus 4 log 2 nu minus nu naught over delta nu Doppler squared. So it's got a Gaussian line shape. And delta nu Doppler depends on temperature, so it goes as 8 kT log 2 divided by the mass of the atom, c squared. It's kind of fun to see an mc squared in an equation. Makes you feel like Einstein here. Then times nu naught. So heavy atoms have a smaller Doppler broadening. Light atoms have a big one. So mercury is fairly narrow. Helium's huge. Scales is the square root of the temperature. So you want to reduce Doppler broadening, you cool it, but it's very frustrating. Go from room temperature to 77, your Doppler broadening drops maybe by half. You go to 76, everything condenses out into liquid. So it's kind of hard to beat this, but you can help it a little bit. So remember, there's your Doppler broadening. This, remember, was inhomogeneous because in this distribution, you got this set of atoms here, and these are seeing a different response. These are Doppler shifted in frequency, so they respond to this frequency. This is in nu, and this group responds to this one, and it's not homogeneous, so you get a variance there. Well, anyway, we talked about the line shape. So we've got these things, we add these G of nu's onto our equations and modify our rate equations appropriately. So we have these things we knew about. We've got these B coefficients. We've got to figure those out. Populations. We have energy density. We're going to talk about that today. How often do you ever characterize a system by its electromagnetic energy density? I never do. So we want to put this into units, which we normally do. We normally talk about intensity. I can measure intensity because this energy density is traveling at the speed of light. It's not just sitting here as a blob. It's gone. So we tend to characterize that in terms of intensity. So we're going to convert this into intensity. We're going to convert this maybe into other units, get everything combined here, and try and make something which is a little more pragmatic in terms of this equation, so we can figure out how this beam is going to change. I put in some intensity here. I get a change of intensity here. Can I predict what that change is? Of course. That's what we're going to do. So that's the goal. So the first thing, notice these are all changes of an upper state. So I can look at the total change of N2 is just the sum of these. I've isolated them to the different processes, but the net effect is N2 is changed by spontaneous emission or by stimulated. Spontaneous, we'll talk about this later, just gets rid of light leaves in all directions. So when this photon leaves, it could go this way, but it could go this way, it can go all over the place. So spontaneous emission does show up in our output beam. Spontaneous emission shows up in our laser beam. It's actually noise. But most of it goes elsewhere. It goes out 4 pi sterads. Whatever a solid angle of our beam is, we capture that fraction of it. It can have any wavelength, it can have any wavelength over this whole scan here. So it's got a big delta nu. It can be polarized in various ways. Now, there's all sorts of things about spontaneous emission which are just purely random. The stimulated emission is going to be in the direction of the beam. So if I stimulate something, my stimulated photon is going to come off that direction, not another direction. It's going to have the same frequency. So if I come in at that frequency, the stimulated photon is at that frequency, in that polarization, in that direction, that phase. It's a perfect clone. And then if I absorb, it's the same thing. If I absorb light, I remove some from this beam, not from other beams. It's just this beam gets reduced, and the frequency and phase and all that kind of stuff depend on what was coming in. It's all linear. So stimulated is more of the, I guess the driven response. This is just random stuff. Nevertheless, these are all the changes in N2. So we can write them all down together, and you get this kind of strange expression, which is not very useful. And so we're going to spend some time modifying it into terms which are useful. So let's just write this down. You've got the total, crud, where is this thing? Okay, here it is. dN2 dt due to anything and everything. It's going to be minus A21 N2, that's spontaneous, minus B21 N2, rho of nu, G of nu, and then plus B12 N1, rho of nu, G of nu. So same intensity, same G of nus, just different populations. So that's the total change in N2. And the reason we're doing this is I've emphasized a change in N2 means a change in photons. And so if I have stimulated emission, N2 is going to, when that goes down 1, I've got one more in my beam. So this is a good thing to start with. Now I got a lot of terms here. So I want to convert rho into units which are useful to us. And I want to convert B into something I can measure. And we talked about how we can measure A. A is just 1 over the lifetime. So can I convert this into that? So remember we talked about, or we didn't, but Professor Jana talked about Planck's law. And Planck's law, Planck went through this whole analysis and he found that the energy density, rho of nu, was equal to 8 pi n cubed nu squared h nu divided by c cubed 1 over e to the h nu over kt minus 1. So there's Planck's law. Now, then we did the Einstein A and B coefficients. And Einstein looked at this population thing and the thermal on this. And Einstein found, when he solved for his rho of nu, just using his kind of technique, he found rho of nu was equal to 8, he used these rate equations, A21 over B21, 1 over B12 G1 over B21 G2 e to the h nu over kt minus 1. I can only imagine that must have been quite a moment when his algebra came out with that, because then he compared the two. He said, same form, that's good. And from this, this just came out of the ABCD analysis. The Einstein A and B coefficients. He just took that box and steady state and solved for all these ratios, N1s and N2s and stuff, compared them to Boltzmann and so forth, and he got this energy density. it's got to be the same as Planck. It's the same kind of system. So you compare these two and you can say, this expression here must be equal to A over B. And so that lets me maybe replace B with something proportional to A. And what I'm going to try and do is get this whole expression in terms of A. I'm going to get all the B's out of there and just go to A's. Yeah?
What is the difference between G1 and G2?
Oh, thank you. So, and that's coming from a chemist. I'm impressed. So G1, remember we have all these G's? So this is the degeneracy G. So this is a degeneracy. And what's a degeneracy? So imagine you've got some atomic transitions. Now I can just put 1s and 2p. You all know these guys here. So 2p can be px, py, or pz. So there's 3 distinct p orbitals, but they all have the same energy. So degeneracy is when I've got different states which have the same energy. So you've actually got a px, a py, and a pz, and I can't draw. But they're all p's. They're all the same, function, except they all have the same energy. So we would say this has a degeneracy of 3. This has a degeneracy of 1. So it's degeneracy means how many states do you have with the same energy? So we'll talk about this in a minute. But what it turns out here, we'll talk about this in a moment. But when I've got 3 states here, I'm populating up into 3 states. So the impact is divided by 3 up here. When I'm doing stimulation, there's only 1/3 as many states which are corresponding to my polarization and so forth. So my stimulated emission rate gets modified by the degeneracy. So we put that in there. Now, I'm not going to expect you to look at a transition and say, oh, this is erbium 3+ in zinc selenide, so the degeneracy must be, no, we're not going to do that crap. If you need to know this, I'll just tell you. We'll just say, okay, the degeneracy of this state is 3 or 2 or whatever it is. We'll always give you that number. But it does affect, we'll talk about that in a moment, it does affect how these things work out. So that's all the G's are. So we had, what do we have? We had G of the stability diagram. We have G of degeneracy, and there seems like there's another G we had the other day. I can't remember what it was, but there's always lots of multi-use of variables here. Okay, so we look at Planck, we look at Einstein, we say, you know what? This is A over B. And so that's going to let me replace this B with something with an A. I'll do the same thing here. And so I'm going to get everything in terms of A. So I'm going to simplify my equations in terms of A. And the reason I like A is because I can measure A. I can go in the lab and determine A. And the reason I can measure A is because it's a lifetime. So that'll be my first step. And how do I convert B's into A's? I look at that, I look at that, and I say, oh, this is pretty simple. I've got that B21 equals this mess, C cubed over 8 pi n cubed nu cubed h times A21. So I can just take B, drop it out, and replace it with this expression.
Wait,
Yeah.
is that n cubed r cubed?
That's n cubed nu cubed. That's bad news.
Oh, okay.
Bad news. So
Okay, is that
nu. So it's n cubed nu cubed h.
oh,
Here we have nu squared h nu. I just lumped the nu's together. So, but anyway, you see how to do this. You can see that there's a way to relate A to B. Now let's look at this term here. I've got that big ratio here. I'll just emphasize, I've got a 1 here. So the only way this can satisfy Planck is if this ratio equals 1. So what that tells me is that I can relate B12 to B21. So B12 equals B21 times G2 over G1. So the stimulated absorption and emission rates are identical except for the degeneracy. If they have equal degeneracies, if they both have a degeneracy of 1, then it's just as likely to go up or down. It's the same rate, same strength. But if I have a different degeneracy, let's say the upper has twice as many states here, then this is going to be twice as big as that. So there's going to be there's going to be twice as many going up because I've got 2 states, each going down. So 2 states at half going down is equal to 1 state of 1 going up. And so it's a balance equation basically. But what this lets me do is relate B12 to B21, but I can relate that to A. So I can put everything in terms of A. So there's my first step. So I'm going to do that in a minute. Now, before I get there, I want to look at rho. And rho is, as I said a minute ago, rho is energy density. So we got this blob of energy, and it's electromagnetic. Now, if we're sitting inside a cavity and things, it's not static, it's moving all the time, as you know. So, but it's sitting there. We have this energy density. But in our beam, wherever that is, what we actually have is we have this column of photons. They're zipping along at some velocity, some phase velocity, or some group velocity. So I could take a section of this, just grab a chunk of laser beam, and there's going to be a certain amount of energy density in that. It's going to have some joules per meter cubed, but it's zipping along the speed of light. And so it's cruising at that speed. So if I were to sit here at some plane and see how much power is blasting through, I would call this intensity. Intensity is watts per meter squared, or joules per second per meter squared. So what's intensity in terms of this? Well, it's just simply equal to rho times c. So intensity is just my energy density times, we'll call it the phase or the group velocity, or rho times c over n. So I can convert, and what I like about this is I can now convert rho, which is just some nice number up there, into an intensity of my beam. And I'm going to come in with a beam, which I know I've got some laser beam here. It's going to go shooting through this thing. And if I've got an intensity of I, it's got an equivalent energy density of that way, or written a bit differently. Rho can be written as I divided by c over n. So I can put rho in terms of units which are more practical to measure and more relevant to the issue at hand. Okay, so I'm going to replace rho and I'm going to replace b. And we're going to go through and do that. So we get, it's going to be kind of messy here. I'd like to do this. Try it this way. Okay. Because we're going to manipulate it and kind of convert it into different forms and come up with a cross section. So we've got a little bit of magic to do. Okay, so let's write this down. So I'm going to go up here again. I've got dN2 dt equals, I'm going to convert everything into A's. So my first one's easy, A21 times N2. I'm done. Spontaneous emission, got it, it's under control. Now, here we're going to have, okay, let's just do one step. B21, N2, rho of nu, G of nu. Okay, B2 equals, crap, did I cover it? Okay, B2 equals this. So let's look at that term for a minute. And instead of just brute force plugging it in, I want to manipulate it a bit. So I've got B21 equals, so we've got a C, let's do it like this, C squared over nu squared. I'm going to pull a C and squared nu squared out. I'm going to have a 1 over 8 pi n squared. I'm going to have C over n. I'm going to have 1 over h nu. I have an A21. So that's that, just kind of expanded. Make sense? So I've just kind of segregated the terms. This you might recognize as wavelength. So I can write this as lambda squared over 8 pi n squared. That lumps these two together. I've still got the C over n. We'll come back to that in a minute. And then I've got 1 over h nu times A21. Okay, so there's B21 in terms of wavelength. And wavelength's a much more practical way to operate when you're in the lab. You know, I don't know the frequency of this green laser, but I happen to know it's 500 nanometers. So wavelength is more convenient for us. So we do that in wavelength. So we got these terms here. Now let's look at, so I'm going to have B and I'm going to have times a rho. So let me take B times rho. So when I multiply B times rho, and for rho, I'm going to use, I guess I lost it here. I'm going to use I over C over N. So this equals B times I over C over N. Oh, there's a C over N. Interesting. Yeah.
So N is the index of reflecting, right?
Pardon me?
N is the reflecting index?
Yes. Yes. Yeah. So, I pulled. I had 3 of them up here. I pulled 2 out. I kept 1 here. And then I noticed that my intensity, my rho is equal to I over C over N. And so if I plug in for rho, I equals C over N. If I plug this in for rho, the C over N's cancel. And so those drop out. And so when I multiply this by rho, I'm going to be multiplying it by I over C over N. So this is my rho term. So this is B21 times rho. Rho is in units I like. And I kind of segregated that out because I'm going to see it over there. So those guys kind of disappear. And that simplifies things a little bit. And now I'm going to plug all that back up into this thing. And so this becomes, minus A21, N2 minus, let's start doing some substitutions there. So I'm going to get A21 lambda squared over 8 pi n squared. G of nu, I'll bring that down. Now I've got to get my rho in there, so rho just becomes I, and I've got this H nu sitting here, which I got to keep in there. And then I've got N2. So this becomes that. So all I've done is I've converted B into A and rho into I, and I get this form here. Now, you're going to get to know and love this well. You'll have this formula memorized pretty soon, but we're not quite done. We also have this term here, plus B12 and 1 rho of nu, G of nu. So we're going to do the same thing. And what we're going to find, and this should not surprise you, is we're going to get all the same terms and all the same manipulations here from the B12 rho. We're going to add a couple of degeneracy terms, and that's about the only difference here. And there's an N1. So when you get all done doing this, it turns out you get all this crap here, but it's multiplied by G1, G2, N1. So all we do is this minus G2 over G1, N1. And now we have that top expression. We now have this expression all in terms of A. So it's the same thing. DND2 still the same process. I've got spontaneous, stimulated emission, and absorption. I've rewritten my B coefficient in terms of A, and I've got the wavelength in it now. I've got my line shape function. I've got the intensity at which I'm probing, divided by h nu. This is an interesting number, I over h nu. That's how many photons are in the beam. It kind of tells me, I've got n photons in this beam, which is kind of interesting. And we're dealing with n's. So it's just neat how that works out. And then I've got how many atoms in the upper state, how many in the lower state. Okay? So that's a very nice expression. So this is really critical. So we have spontaneous and stimulated. Now, we usually will go ahead and make a definition here. We're going to call this thing here the cross section. So this is a definition. And if you look up and read a paper on lasers, they usually will tell you what the gain cross section is, and they're referring to that parameter right there. So this is the cross section. So A21 lambda squared divided by 8 pi n squared G of nu is sigma of nu. Sigma is the gain cross section. Typical values, rare earth atom might be 10 to the minus 21 square centimeters. A really wild dye molecule might be 10 to the minus 12 square centimeters. So they range quite a bit. But look in the, typically, I'll say 10 to the minus 14 to 10 to the minus 21 is kind of typical. And this is in square centimeters. And they usually are given in centimeters. I don't know. That's why I use centimeters, because you usually find your cross sections in centimeters. Centimeters is an area. So what this says is you can treat your atom as this unit of area. And your photons are like particles, and you're shooting photons in there. And what are the chances the photon's going to go by? Is it going to zip past it or smash into it? The bigger the area, the more likely you'll interact. The smaller it is, the less likely. So it's a very physical picture, and it's very. I really like this in terms of photons, because we're not worrying about dipole moments and computing the quantum transitions of an atom. It's just clay pigeons and the shotgun. You got clay pigeons up, then you're shooting pellets, and you hit the bird or you don't. So it's really a very simple, very particulate kind of view of this stuff. But anyway, the cross section is something you'll get to know. A lambda squared, given by that. I'll give you an example. We were in the lab. It's very easy to do. We were in the lab. We got sodium chloride sample. I put color centers in it, went in and measured it, and within about an hour, I took a spectrum. I got the spectrum like this. It had emission at 1.5 micron. It had a bandwidth, a delta lambda, which we converted into about, say, 10 to the 13th hertz. You get your delta lambda. And we measured the lifetime. And this was a two-level system in an upper-lower state. So we pulsed it, put a whole bunch of atoms up here, and then just watched the decay as it came down. And we saw the decay. It was about 160 nanoseconds. Okay, so that took about an hour to do all that. I now know the cross section. So how do I know it? Okay, look at this formula. Okay, A21. So N2 goes as N2 naught e to the minus A21T if I only have two levels. This is the ground state. So I can determine by, this tells me that A21 equals 1 over tau. I measured tau. I know A. I measured A. So that was easy. So for this sodium chloride system, we immediately know, I know A was 1 over 160 nanoseconds. Okay. What else? I need lambda squared. Well, that's pretty easy. I need this in square, it's cross sections in centimeters, so I'll put the wavelength in centimeters. So it's 1.5 times 10 to the minus 4 centimeters squared. 8 pi, everybody knows 8 pi. The index of refraction for the sodium chloride is about 1.5. So I put that in. G of nu. What do I do for G of nu? So here's where I can be very precise and accurate, or just first order. To first order, I say G of nu is 1 over 10 to the 13th. I'm just going to approximate my line-shape function like that. Is it accurate? No, it kind of underestimates the peaks, but it's within a factor, at 30% or something like that, so it's good enough. So it's a good first shot. So G of nu, 10 to the minus 13. And there's my gain cross-section. So there's nothing magic about this number. You can go in the lab and pretty quickly determine sigma. If I give you a sample, you just have to measure a couple things about it, and you can walk out of this saying, the gain cross-section for this is 10 to the minus 18 or whatever. So it turns out this one, I forgot, I didn't do the numbers. It was on the order of 10 to the minus 16, which is a pretty high gain system. So, but it's very simple to do. So don't be intimidated by these words cross-section or that kind of stuff. It's just very simple to do. And this is a really nice formula. I mean, this is a formula we just carried in our heads in the lab. And in the lab, we're saying, God, what's cross-section? You can just, it must be about this. And so there. Now, what do you do with it? Well, we'll talk about that in a minute. But that's the first thing to know. So here we have this thing here. Now, how do we use this? So we want to get gain out of a laser. And so what we're going to do is take a population and run a beam through it. So got some population here. Let's make this a delta Z. And here I've got an N2 and an N1. And we're going to bring a beam in, some intensity. And I'd like to know what's the intensity leaving. All right, so here's to go back to this business. I don't have an equation on DI. I have an equation on DN. But here's the key thing. When delta N2 corresponds to delta, I want to say the number of photons. So if N2 goes down 10, I've just generated 10 photons. Does that make sense? So there is a direct correlation between the change in number and the change in photons. And the change in photons is going to be a change in intensity. So that's where we get this going. So what we do, here we have N2, which is number of atoms per meter cubed. I want to convert that dN2, so I run a beam through here. I'm going to change the number of atoms in that volume. Now, how do I convert that to intensity? Intensity is, think about intensity as a whole bunch of photons sitting here, and they go blasting right on through. So they just, they sweep the thing out. So intensity is a plane, but intensity is not in a volume. So the intensity is the plane. And so this intensity is coming along, and it's going to sweep that volume out, and it's going to end up over here. And so what ends up doing is you end up converting to get from dN dt into a di dz. What I want to do is, here I've got dz. So what I want to figure out is what's di dz. And what I've got is in dN dt. Well, the intensity is flying through here, and the dt times the speed of light gives me my dz. So the conversion from dN dt to di dz comes out because I'm sweeping through this thing. I'm kind of going from a 3D space to a 2D because of the intensity. And what happens is that your equation then becomes di dz instead of dN dt, and it follows all this stuff. And it's just due to stimulated emission. I'll just put the stimulated emission part down now. A21 lambda squared 8 pi n squared g of nu times n2 minus g2 over g1 n1 times I of nu. So this is my change in intensity due to stimulated emission. Here's my stimulated emission, there's my absorption. Here's the gain cross-section. And then the conversion from T to Z happens because we've got this intensity flying at the speed of light, and that's where that conversion happens. So this is now this is the kind of the carry-away. This is the big equation for the laser. Intensity does change, notice I don't have any stimulated emission here. And that's because there is stimulated, I have no spontaneous emission here. There is spontaneous emission. Most of it's going elsewhere. Imagine I got this beam and I put a pinhole here and the beam goes right on through it. So the beam is nice and collimated, flashes through. This is going to block most of the spontaneous emission. I only take the solid angle here. There's a solid angle of this beam, and I divide it by 4 pi, which is the solid angle of all the light. That's the fraction of spontaneous emission which gets through. So this solid angle is typically 10 to the minus 3, something of that nature. So we're talking about a reduction in spontaneous emission on the order of at least 10 to the 4th. And then another issue I can look at, if I've got this atom or the system that's giving off spontaneous emission over this incredible delta nu, my laser beam probably has a very narrow very narrow frequency, nu here. So I could in principle put a filter here, a bandpass filter, and I could also eliminate all spontaneous emission except which happens here. So I'm just going to get kind of a G of nu term for my spontaneous emission through that filter. What's the probability it comes in that filter? No, it's a g of nu. So my spontaneous emission gets reduced by spatially, and it's going to get reduced spectrally. And if I really want to get to be a jerk about this, I can put a polarizer in, because my stimulated emission will be polarized. My spontaneous emission tends not to be, so I can kick another factor of 2 there. So there's all sorts of ways I can kind of filter the spontaneous emission out. And so it turns out that in terms of intensity, I really don't measure any change in intensity due to spontaneous. So I'm only retaining the stimulated term, because the spontaneous term is pretty trivial. It's critical for getting the laser going, and we'll talk about that later, but you've got this laser cavity. We're going to put this material in it, which has an N2, and you've got there, and it's happy to amplify something. But if there's no beam, where's the chicken, where's the egg? Where's this beam it's going to amplify? It needs something to amplify. And so what happens is there's spontaneous emission going off in all directions. One lucky photon hits the TEMQ mode, which happens to be resonant, and that photon now goes back, it's amplified, and it's the seed, it's the Eve. It's the mother of all photons. So everything follows from that. So spontaneous emission is necessary to get things started, but once it's going, it's not a significant contributor. Anyway, there's our gain equation. Now, this is cross section. So di to z equals sigma. Now let's look at this: N2 minus G2 or G1 N1. Okay, this is the population of these various levels. So here's an energy level diagram. Here's N2, here's N1. There might be some below it. N1 doesn't necessarily have to be the ground state. In fact, it usually is not. If this were a thermal situation, if this were this light bulb up here, the population, what would the population of N2 be with respect to N1? Would it be smaller or bigger? If it's a thermal population? Smaller. Yeah. So we have, typically you'll try and find kind of a Boltzmann distribution in population. So here's your probability, and here's energy. So you'll have a lot of N2, not so many N1s. So what that means in a typical system, a typical thermal system, your change in intensity is going to be the cross section times a negative number, because this is smaller than that, and so you're going to get basically di dz equals minus gamma I, where gamma is all this crap here, and of course that's going to give you attenuation, and that's what we see in most stuff. You shine light through material, less light gets out the other end than went in because there's attenuation, there's absorption. Or scattering, but let's look at absorption. So a typical thermal natural situation absorbs light. Stimulated emission is not common, and so that's why the laser was not, obvious to anyone initially. What you need to make a laser go is to have more atoms in N2 than N1. So that's a non-thermal situation. So you need to have a big population here of N2 and a small population of N1. Clearly non-thermal. So this is called a population inversion. And it's called an inversion because it's not your normal thermal distribution. So you say, what's the inversion? Someone will say, what's the inversion? How big an inversion do we need? How big is N2 minus N1? If I have N2 minus N1, if N2 is somehow bigger than N1, this now becomes a positive number. And now intensity goes through and gets brighter as it goes through. So you actual gain. And so that's a very important part. So this equation is kind of the foundation of the laser. Here you've got your cross section, and it's completely determined by the atom. The atom is going to determine what its spontaneous emission rate is and wavelengths. The inversion is you. You're going to create the inversion somehow. You're going to find some way to upset this natural scheme. This is called pumping. So we have to. This is where the magic happens. We've got to find some way to excite a lot of these atoms without exciting those atoms. And so we'll talk about how you do that. You can shine light on it or whatever. But once you've got that, you've got gain. And so long if that's positive, and you got a decent number here, you've got gain. And how much gain? Well, you just plug the numbers in. Let's say I've got let's say sigma is 10 to the minus 18. So, and I've got an inversion, and I go and look at my inversion, and my inversion is 10 to the 17th per square centimeter, per cubic centimeter. So sigma 10 to the minus 18 times 10 to the minus 17 would be 10 to the minus 1. So I'd have a dIdZ of 0.1, what am I doing here? Yeah, 0.1 I. And times the length, you know, so that means my dIdZ. So I'd multiply that by or integrate it over my length, and I can figure out how much amplification I get. So once I've got my cross section, I have a pretty good idea how big the inversion has to be to get the gain I want and take it from there, and vice versa. All right, I think we'll stop there. I think we're, yeah, question?
Yeah, are we assuming that these population densities are uniform volume?
Yeah, in this one, yeah, in here, N2 is the volume per cubic centimeter, or the number per cubic centimeter. In practice, no. You know, if I mean, one way you pump, a good way to pump, what is class? It's class over at 11, right? Oh, I thought it was over. I was wondering why no one was closing their books up. So I thought you were, anyway, a very popular way to pump is to take a crystal and pump it with a laser beam. So you've got a situation where your beam's like this, and so your population will follow that. You'll have a higher density in the middle of the beam than on the edges. So you have a non-uniform density. So yeah, and then so you'll get variance in gain as you go across this location. That's very common. And usually we want that. You know, you can take I mean, if we were to make a laser out of that light bulb there, then you've got a cross section, and that's fairly uniform. This is the helium neon laser. You know, all the atoms are excited, and your mode is sitting right here. So what's happening is you're using the gain there, but all this other gain is unused. And that's why you tend to see higher order modes kick in, because there's this gain sitting there that's not being used. Ideally, you want to put your gain right where the mode is and no place else. So that's why optical pumping is nice if you can pull it off, or some sort of magic with electricity. You know, a semiconductor laser, those are made with p-n junctions. So you have a p and an n. You put a lot of current into this thing. The way you do these things actually is you create these little kind of quantum well traps, and so all the electrons fall into there, the holes there, and they're localized in about 100 angstroms, and so you got everything in the right spot, and so your gain is very localized there. Then your mode kicks in and extracts it. So there's a lot that goes into the engineering of how do I get my gain where I want it, so it's best used. But in these equations, we are microscopically assuming it's uniform over an area. It'll be obvious when you do a problem how to deal with that. All right. Any questions about this stuff? Let me just give you a quick example. I got 2 minutes. So, how do I pump? How do I pump? I want to find some way. We call pumping is the way we create an upper state. Let's say I only have 2 levels. So I've got a ground state and an upper state here, and this is the ground. And I'm going to pump by shining light on it. I'm going to put it in Einstein's little box. I'm going to crank up the temperature, and just excite the daylights out of this thing. So we know that we're going to have light shining on this thing, and that's going to absorb and raise atoms up. And so if you write the expression, dN2 dt it's just going to be minus A21 N2 plus sigma I over h nu. I'm going to use this new notation times N1 minus sigma I over h nu N2. So stimulated or spontaneous emission reduces it, stimulated emission reduces it, absorption increases it. So notice I've got sigma I over h nu. I'm taking advantage of all this stuff we just done. So there's the new rate equation. As I crank up the intensity, I clearly am getting more absorption and bringing it up and so forth. And I want to set that to equal to 0 and see what my equilibrium is. So you set it equal to 0, and you solve for this, and you find that N2, where did I get this here? You get N2 is equal to, and you can do this, it's going to just do it today at lunch, sigma I over A21 h nu plus sigma I. So times, we need some, This is N2 over N1, sorry. Okay. So you can solve for the ratio of N2 to N1 in this situation. And notice that this is always less than half. You know, at the best I could do is equalize the population. I'm going to infinite intensity. I would equalize N1 and N2. But I'm not. So if I only have two levels, it's impossible to get an inversion. I can't get an inversion with two. There's just no way I can kick anything up here, because any process which kicks an atom from here to there works reciprocally and will with equal likelihood kick it back down. The stimulated process is always reciprocal. So with a two-level system, there's no way I'll ever get an inversion. So the only way I'm going to get an inversion is have a third level and somehow pump to that third level and then let it relax down. And then, or I get them up here and keep that one empty. So we need multiple levels to get inversions. So we'll talk about that later. But the key thing, just looking at these rate equations, you can convince yourself pretty quickly that a two-level system, you'll never get an inversion on it. So you have to have multiple levels to get these inversions. Okay, we'll stop there and we'll put this in a cavity on Wednesday and make a laser. So you're ready for the laser now.